Hello and good afternoon, friends. Welcome once again to the CEC-UGC live lecture. Dear friends, in this session today, we would be talking all about chemistry for all the students of chemistry. Once again, we have brought for you another important topic, and the topic today is reaction mechanism. I would say rather it is a series. We would be conducting numerous sessions on this particular series, that is under the series reaction mechanisms, and today basically we are going to talk on radical reactions, halogenation of alkenes. So for this we have again with us in our studios Dr. Aparajita Chauhan. Dr. Chauhan is Associate Professor in Department of Chemistry, Sri Aurobindo College, University of Delhi. So dear friends, let's take advantages from our experiences and try to understand about radical reactions. As I already said, we would be specifically going to talk on halogenation of alkanes. So first of all, I would like to welcome our guest Dr. Aparajita Chauhan.
Good afternoon, thank you so much. And today we'll be continuing with where we left last time. If you remember, last time we had, in our previous series, we had talked on reaction intermediates. So taking from there, today we will be talking about reaction mechanisms, that is free radical reactions. So if we talk of free radical reactions, these are very, very important reactions. What are radical reactions, or rather what are radicals? Radicals are species which have one unpaired electron. Remember, these are different from oxygen, in which we have a pair of unpaired electrons. We have an unpaired there of electrons there, whereas in radicals we have one electron, odd electron, so they are very, very reactive. They are involved in ozone depletion. When we talk of ozone hole, what are the type of reactions which are involved there? Again, radical reactions are involved. If I talk of aging, free radicals are involved. If we talk of cancer, which is unstopped growth of cells, again it is a free radical reaction. Not only this, if I talk of polythene, which is a polymer whose molecular mass can vary from few thousand to millions, is again, it involves a free radical mechanism. We know polythene, from polythene we can make bottles, plastic bottles, and from polythenes we can also make knee replacement joints, etc. Not only this, free radicals are also involved in different biological systems. That is, they are involved in drug messaging or drug targeting. And there we have some very important chemicals in our body like vitamin C and ascorbic acid, which doctors normally tell us to take when we are ill, because these are the species which are free radical scavengers. That is, they destroy free radicals, and that means they stop their reaction. So when I'm saying they stop their reaction, what do we mean by this? That is, free radical reactions can be of two types basically. They can be substitution reactions or they can be addition reactions. So today we'll be talking about a free radical halogenation of alkanes. So now what we see is that when I talk of a free radical halogenation of an alkane, we can have methane and chlorine in the atmosphere. Nothing happens. They're just lying there. I take them in a test tube. Nothing happens there. So why doesn't anything happen there is because they need a certain amount of energy, that is energy of activation for them. So before we proceed further, you have to remember that when a bond breaks, that will involve a bond dissociation energy, and the cleavage of bond is an endothermic reaction, whereas when a new bond is formed, that is an exothermic reaction. So when we see here methane and chlorine, they are just happy being there. Nothing is happening there. Now supposing we provide energy in form of light to this chlorine molecule, and this chlorine molecule absorbs that photon of light and its vibration increases, and maybe then this chlorine molecule would break. Or other thing that we can do is, if we want to conduct this light in reaction in dark, then we can give it enough of energy so that the bond cleavage takes place here. So now when we talk of this reaction where the bond cleavage is taking place here with the help of heat or with the help of light is the chain initiation step. And in this reaction, please remember, only bond is breaking. And what I've shown here is with a half arrow that this is one chlorine is taking one electron and the other atom is taking the electron which it had contributed towards bond formation. And what do we get here is our free radicals. So now free radicals are very reactive since they have only one odd electron. So what they need now is one electron to make this bond. And the bond dissociation energy here is 243 kilojoules per mole. This is the amount of energy that we require to break this bond. Now once this chain has started, the chain initiation has started, now what we have here is a chain propagation step. What happens in a chain propagation step is this free radical, which is short of one electron, will now react with another molecule of methane. So what it does in this process is it tries to convert itself into a molecule, whereas making a new free radical, that is methyl free radical here. So what we see here is in chain propagation step we have two reactions involved. One, here what is happening is a bond is being broken and a bond is being formed. So what we on the left hand side also we have a free radical, whereas on the right hand side also we have a free radical. Now the other option is that this free radical may go and react with another chlorine molecule and take a chlorine from there, converting itself into chloromethane and in turn generating another free radical. So what happens in chain propagation is, in chain propagation, a free radical is reacting with the molecule and in turn generating another free radical, which again goes and reacts with another molecule. So what we see here is that this is a chain reaction. How can we say it's a chain reaction? Just by having just very few atoms of chlorine or chlorine free radicals with the help of very little amount of light, this chain propagation, or we can have thousands and thousands of product molecules in this. Not only this, but the second point we can say that this is a chain reaction is, supposing now in the last step, which is the chain termination step, what we find here is that two free radicals react among themselves to give us a neutral molecule. So this chain termination step is an exothermic reaction. What is happening here is that methyl free radical is reacting with a chlorine free radical to form chloromethane. The second option that we can have is that two methyl free radicals react among themselves to give us ethane, and then what we can have is that two chlorine free radicals react to give us a molecule of chlorine. So again what we have is, when now what we see here is not only this happens, we can have a number of multiple reactions also. Initially what will happen is that there will be reaction between chlorine and methane, that is chlorine free radical and methane, and we will have enough of methyl chloride formed. Once we have enough of methyl chloride in the reaction mixture, now the probability is that this chlorine free radical which we have, it may go and react with a chloromethane molecule here. And in this process what it does now here is that it abstracts again a hydrogen free radical from hydrogen atom from here and is converted to hydrochloric acid, and in turn generates a chloromethyl free radical. Now this chloromethyl free radical goes again and reacts with the chlorine molecule when we have chloromethane and chlorine free radical. So what we see here is that we have number of side reactions are going on simultaneously. That is, first case chloromethane is being formed. When enough of chloromethane has been formed, it may go and react with another chlorine free radical and itself be converted into dichloromethane. Now what we see is, when we have enough of dichloromethane in the mixture, now we have three probabilities. One is chloromethane, formation of chloromethane, second formation of dichloromethane, and third probability is, now this goes and reacts with another chlorine free radical when we get a dichloromethyl free radical. This dichloromethyl free radical again reacts with the chlorine molecule and we get a trichloromethane. So in such a process what we get is we get a multiple products, that we get methane, chloromethane, dichloromethane, trichloromethane and tetrachloromethane. So just by doing halogenation what we are getting is umpteenth number of products. So can this reaction be stopped? This reaction can be stopped by a chain termination step, or these radicals we can say can be stopped if we add a free radical inhibitor to the reaction mixture. That is, if we add oxygen to this mixture, oxygen will react with methyl free radical to give a peroxymethyl free radical which is stable. Similarly, what we find in biological systems, we have enzyme superoxide dismutase, enzyme peroxidase, ascorbic acid, which act as free radical scavengers. Not only these, the pigments like lycopene, they also act as free radical scavengers. Phenol acts like a phenoxide ion, acts like a free radical scavenger. That is, it will react with the free radical and convert it into a stable free radical, which will not be as reactive as these methyl free radicals or halogen free radicals. Now we are saying that this reaction is probable or this reaction is not probable, where this reaction will go to completion or this reaction will not go to completion will depend on the energy requirement of the reaction. So what we know is, when we see a reaction, we know that when a bond dissociation takes place, it absorbs energy. That means it is an endothermic reaction. And when a product forms or when a bond forms, that is an exothermic reaction, that is, energy is evolved during this reaction. So what we see here is, in this reaction, if I talk of this propagation step here, what we find here is that chlorine free radical is reacting here and we are getting a free radical here. So what is happening here is a bond is breaking between C and H. So there will be some bond dissociation energy here, and a bond is being formed between C and H. So there will be some bond formation energy here. So difference between these two energies gives me what? It gives me as the energy of the reaction or the heat of the reaction. This will be now taking into consideration. Second point, what we find here in this reaction of methane with chlorine, there is not much change in the entropy of the system. And if there is not much change in the entropy of the system, then we say whether the reaction is going to be feasible or reaction is not going to be feasible, or how reactive it is going to be, will depend on, we presume it will depend upon the energy of activation. So first of all, what we have to do is we have to distinguish between what is heat of reaction and what is energy of activation. Heat of reaction is the energy difference, that is the energy evolved when the bond is being formed and the energy required to break a bond. That difference is known as heat of reaction. And energy of activation is the energy difference between the energy of the transition state and the reactants. So these two energies are very, very important when we understand this concept. And please now be with me 100% so that we can understand it better. So now we can, from the heat of dissociation and heat of formation, we can calculate the overall heat of reaction. So now what we see here is, when I talk of an endothermic reaction, then in an endothermic reaction, the bond is being broken. So the first step, which is your chain initiation step, this is an endothermic reaction. In this case, we will have to give this system energy equivalent to 243 kilojoules so that this bond will break. This is the bond, this is the energy of reaction. Now let me go, when we see the step 2. Step 2 involves two reactions. One is, the propagation step involves two steps. One is in which Cl free radical is reacting with the methane molecule. Here what we find here is that the dissociation energy for methane is 440 kilojoules per mole, whereas the bond formation energy here is 432. That means if we calculate the difference between these two energies, this reaction is slightly endothermic reaction, right? That is, it is endothermic by it will require 8 kilojoules of energy per mole will be given here. Now, if we talk of the next step in which methyl free radical is reacting with the chlorine molecule, here in the formation of chloromethane, 352 kilojoules of mole energy is evolved, whereas the energy requirement is 243. So the difference between these two gives me minus 109. So this is an exothermic reaction. Exothermic means that the heat is being evolved. So this reaction, overall reaction, is an exothermic reaction. Now if we talk of the chain termination step, this is an totally exothermic reaction, because in this no bond is being formed, bond is being formed, no bonds are being cleaved here. So what we find for the different steps, we have the bond dissociation energies which are equal to the heat of reaction. Now if we go back to the propagation step, how would we find out what is the total heat of reaction for that? Step is, we will add both the reactions, both the propagation steps, that is propagation 1 step and the propagation 2 step, and then we will calculate the heat of energy from this. The energy difference between the two steps is minus 101 kilojoules per mole. That means this step is an exothermic step. So propagation step here is an exothermic step. Now we come to the next concept, which is activation energy. What is activation energy? Activation energy is measured by taking difference in energy of the transition state and the reactant molecules. If we say that the energy of activation is low, that means that that reaction will take place easily. And if we say that the energy of activation is high, that means that reaction will take place with difficulty. And if energy of activation is low, then we say that the reaction will go to completion. But now we cannot measure the energy of activation directly. We cannot determine it from or calculate it directly from the heat of reactions. We have to keep certain points in mind. First of all, what we have to keep in mind is that if in a reaction only bonds are being broken, then energy of activation will be greater than 0. That is, even if a strong bond is being formed in the course of the reaction and the reaction is exothermic, still the energy of activation will be greater than 0, because please remember, in the transition state, bond formation and bond cleavage does not take place simultaneously. First the bond breaks and then the bond formation starts taking place. So there is a little time lag between the two. So this reaction is going to be endothermic. Now supposing we have a second category in which their bond formation is also taking place and a bond cleavage is also taking place. In such a case, energy of activation is going to be higher than the heat of reaction or the energy of reaction. Why so? Because please remember, if we look at these two reactions, then what we find here is that the heat of reaction is 440 and 432. 432 is the bond association energy, whereas 440 is the bond cleavage energy. So here the heat of reaction is 8 kilojoules per mole, whereas energy of activation is 16 kilojoules per mole. Secondly, in the second part, also what we find is the bond dissociation energy or the heat of reaction is just 74 kilojoules. That means the energy released during bond formation is less than the energy required for breaking the bond. So this will have slight energy of activation. Then in such a case also, energy of activation is going to be higher than the energy, the heat of reaction. See, now what we have to keep, if we look into these potential energy diagrams, what we observe here is that the energy difference between the reactants and the transition state is the energy of activation. That is, energy of activation here is 16 kilojoules per mole. Whereas if we talk of heat of reaction here, then heat of reaction here is 8 kilojoules per mole. That is the energy difference between the reactants and the products. So this reaction is endothermic reaction. So what we need here is, we need energy here which is equivalent to 16 kilojoules. So the energy of activation is here. Similarly, if we talk of the second graph here, we again see the transition state is higher than the product. So again here the energy of activation is greater than the heat of reaction. So in both these diagrams, if we see, what we see here is that we are going from lower energy platform to a higher energy platform in a path from reactants to products. Not only this, the energy released during bond formation is less than the energy required for bond rupture. Therefore, what we say is the reaction is endothermic and the energy of activation is higher. Now, if I talk of only of a cleavage, that is, only bond cleavage is taking place and that is also taking place homolytically, then what we find here is only free radicals are being formed. So in such a case, the energy of activation, if you see from this graph, is equivalent to heat of reaction. So this reaction takes place quite all right. But if we go on to the next reaction, that is the termination step. This is an exothermic reaction because in this two methyl free radicals are reacting. And here the reaction is the energy of products is higher than that of the reactant is at a higher plateau than the product which is at the lower plateau. So this reaction is an exothermic reaction. So in such a case, energy of activation is 0. So now what we know is that in the chain propagation step, it is slightly endothermic if we talk of chlorination, and if we talk of chain propagation, that is also slightly endothermic, whereas the chain termination step is an exothermic reaction. So depending upon the bond dissociation and the bond association, we can say how much energy of activation do we require for a reaction to proceed further. Now, this was the mechanism of chlorination of methane. Similarly, methane can react with fluorine, chlorine, bromine and iodine, and we can get different products. But are all these reactions feasible? Will all these reactions take place with equal intensity, or will one of the reactions proceed at a lower rate whereas the other will proceed at a higher rate? Now please remember what we said, to decide whether the reaction will take place to completion or at a higher rate will depend on the energy of activation of the reaction. So what we find here is that the energy of activation is different for different halogens. What we find is that fluorine is highly reactive. The reaction may take place with an explosion. Chlorine is all right. It takes place at 300 degrees Celsius. Bromine is less reactive. It takes place at 300 temperature, higher than 300 degrees Celsius. Whereas iodination is a reversible reaction. To understand this concept, why is one halogen more reactive or less reactive than the other halogen, we will again go into the energy profiles of the reaction. What we see, if I talk of fluorination, I have said fluorination is an explosive reaction. Since it is an explosive reaction, why is this an explosive reaction? I'll just explain it to you in a minute. But since it is an explosive reaction, it doesn't mean that we cannot carry out the reaction. We can carry out the reaction, but with difficulty. That is, we will dilute fluorine as well as the hydrocarbon part, that is methane, before mixing them. And then we may carry out the reaction in a reactor which has copper in it. because that will absorb the intense amount of heat which will be liberated during the reaction. Now see, if we look here, for the chain initiation step, what we need here is, because the bond is strong here, what we need here is, this is an endothermic reaction and it requires 159 kilojoules of energy per mole. So this is highly endothermic here. So that means the reaction does not depend only on the bond dissociation. If you go into the chain propagation step, then what we find here is that the second step of chain propagation, in which methyl free radical is reacting with fluorine to give us fluoromethane and fluorine free radical, this reaction is highly exothermic reaction. That is, it is liberating 302 kilojoules per mole here, and in the first step it was liberating minus 130 kilojoules. So that means the overall energy liberated here is 432, and the energy of activation is very, very small here. And what we see here is, during the chain initiation step, the energy of activation is just 159. So this value is very small, which we need only in the beginning to initiate the reaction. So during the course of reaction, in the propagation step, the amount of energy liberated is 432, and if we subtract the two, I think the energy difference will be great. And this amount of energy is just during one course of reaction. Imagine all the side reactions which will also proceed simultaneously, that is, this fluorine free radical, this chloromethane will again react with fluorine to form difluoromethane, trifluoromethane and tetrafluoromethane. So simultaneously we have so many reactions going on in which the amount of energy liberated is 432, which cannot be contained. So this reaction is highly explosive. So that means whether the reaction is explosive will depend upon the total overall heat of reaction. So that means this is a exothermic, highly exothermic reaction. Now if we talk of bromination, bromination is slower than chlorination and of course slower than fluorination also. It occurs at a higher temperature and its energy of activation is small, comparatively small. So what we see here is, since it is occurring at a higher temperature, it will be little less reactive than chlorine. And then what we find here is, okay, the bond dissociation energy here is 193, and the reaction here in the propagation step, the overall heat of reaction is minus 26. So this reaction is slower than chlorine. Now if we go on to iodine, iodination is not feasible experimentally, because Hi found in this reaction, please remember, will even oxidize iodine back. It will oxidize, it will bring about the backward reaction. So what we need here is an oxidizing agent which would remove Hi from the reaction mixture. Not only this, what we find here is the chain propagation step here is endothermic, whereas when we were talking of fluorination, there this step was highly exothermic. So what we find is the chain propagation step is endothermic here, whereas in case of fluorination, chlorination and bromination, this reaction was exothermic. So iodination takes place with difficulty. Not only this, only 2 collisions out of 10 to the power 12 collisions are effective, which will result in a product that will be formed. So what we know now is, when we talk of halogenation, when we talk of the reactivity of halogens, then we know that in a reaction mixture, if we have methane, then fluorine is most reactive, that is, the reaction takes place with an explosion. So we have to use precautions there. Chlorination, we can control the reaction. Bromination is slow, and iodination is a reversible reaction. This is on the basis of the heat of reaction and on the basis of the energy of activation. Now not only this, we see that if we were talking till now, we were talking of halogenation of methane. But what if we talk of halogenation of higher hydrocarbons like ethane, or if I talk of this molecule here which we have on the screen, which is 2-methylbutane, then what we see here is, will these hydrogens react with equal reactivity or with equal probability with the halogen atoms? We have seen that the halogen atoms are differently reactive, but what about these hydrogens also? If you remember, when we were talking about the formation and the stability of the free radicals, we had discussed that the tertiary free radical is most stable, followed by a secondary free radical, and then primary and a methyl free radical. We said the stability of these free radicals was on the basis of hyperconjugative effect. Now here we will discuss the stability of these free radicals on the basis of the bond dissociation energies. So if I look into these molecules, that is if I look into isopentane, it has 4 types of replaceable hydrogens. Like if I talk of this hydrogen and these hydrogens, these 6 hydrogens are equivalent, that is they are primary hydrogens. Then this hydrogen is a secondary hydrogen. This is again a secondary hydrogen, but this hydrogen is different from here because this was a tertiary hydrogen here, and this is a secondary hydrogen, whereas this is again a primary hydrogens. These two, this and one, are primary hydrogens, but these 2 primary hydrogens are different because here we have a substituent and here we don't have a substituent attached here. So how many types of replaceable hydrogens do we have here? 6 are of one type, then we have 1 tertiary hydrogen here, 2 secondary hydrogens, and again 3 primary hydrogens here. So now if I look into the probability, I'll say I have 6 probabilities here, 1 here, 2 at this position, and 3 at this position. So that means the probability of forming this product, that is 1 chloro, 2 methyl butane, are more if I carry out the chlorination. But what we've seen is that the probability of forming these free radicals is not same. It will depend upon the reactivity or on the potential energy of the free radical. What we see here is that if I have to make a methyl free radical here, so if I have to make a methyl free radical, the energy required to make a methyl free radical is 104 kilocals per mole. Whereas if we look into ethyl, it is 98, and similarly in ethyl, so this energy here is lower for making ethyl free radical, is lower as compared to making a primary free radical. And what we know, and since still if I go on to a tertiary free radical, here the energy requirement is still less, that is it is only 91 kilocals per mole. So what do we know here is that the energy requirement is low, that means the potential energy of this molecule, of this free radical, will be less. That means the potential energy of tertiary free radical will be least, followed by secondary free radical, and then followed by primary free radical. That means tertiary free radical is most stable and it will stay in the reaction medium for more time. So the chances of effective collisions will be more and the chances of getting product will be more. This is what the logic says. Now if we go on to, that means the formation of tertiary is easier as compared to secondary, as compared to primary. Not only this, that means now all the molecules or all the molecules of chlorine, bromine, they should be equally reactive towards alkanes? Then the answer is no. What we know is from our experiment and from our daily life also, one which is more reactive is less selective. That means chlorine will be more reactive, but it will be less selective. That is, if I have a probability here, that is, if I have a molecule, if I talk of isopentane here, and if I look into this molecule, then the probability of chlorine reacting here with primary free radical or a secondary free hydrogen or a tertiary hydrogen, it is equal. Whereas if I talk of bromine, which is less reactive, it will be more selective. for example, if I talk of chlorine, then its order of selectivity for primary, secondary and tertiary hydrogens is, that is, it has a probability that the effective collisions will be 1 with a primary hydrogen, 3.8 with a secondary hydrogen and 5 with a tertiary hydrogen. So that means it is comparatively less selective, because the ratio 1 is to 3.8 is to 5 is not much if we compare it with bromine. Bromine, the probability here is, the selectivity here is 1 is to 82 is to 1600. That is the probability that it will react with a primary hydrogen is 1, with the secondary hydrogen 82 times, and 1600 is for tertiary. That means if in a molecule I have a primary hydrogen, secondary hydrogen and tertiary hydrogen, chlorine can react. There the probability of reaction will be more. It can react with primary hydrogens if the primary hydrogens are more. But if I talk of halogen, of bromine, then bromine is more selective. So there, in spite of primary hydrogens being more, we will get more of tertiary product because it is more selective. So what we've seen here is, in this, what I've done here is, like if I talk of monobromination of propane, then in propane we know that it has 6 primary hydrogens and 2 secondary hydrogens. So now for primary hydrogens, the probability for chlorine is 1, whereas for secondary hydrogens it is 3.8. So now here this is 1 is to 3.8. So the total reactivity that we can have here is 6, and then I multiply 3.8 into 2 because the chances of secondary hydrogens here are 2. So this is 6.6, 7.6 and 6. If we add, the total probability is 13.6. But out of 13.6, the chances of getting primary hydrogen are 6. So here what is playing more important role here is the probability factor, that is the number of hydrogens are important here. So 6 upon 13.6 into 100 gives me the percentage yield of 1 chloropropane, whereas this 7.6 upon 13.6 gives me the percentage yield for 2 chloropropane. So what we find here is that the ratio is almost equal, that is, it is 6 is to 7.6. So here what is playing importance here is the probability factor. But whereas if we look into monobromination and we look into isobutene, then what we find is it will give us major product will be tertiary bromochloride, because here the order of selectivity will be 1 is to 82 is to 1600. So when I talk of probability of primary hydrogen to tertiary hydrogen, there the selectivity order is 1 is to tertiary. And what we find here is that tertiary bromobutane will be the major product, whereas in chlorination the product was almost same. So we say in chlorination what is playing effect is the probability factor, whereas when we talk of bromination, what is playing important there is the selectivity factor. Now if we talk of, now we have to go into the stereochemistry of the molecule. Now if we go into the stereochemistry of the reaction and we say that during the course of reaction a chiral center is generated. So what we find here is, if we take pentane, pentane is achiral. That is, it is not optically active. When I say it is not optically active, that is, it does not have a chiral carbon or it does not have an asymmetric carbon. What is a chiral carbon or what is an asymmetric carbon? It is a carbon which is attached to 4 different groups. So this molecule is achiral. And here the reagent is also achiral, that is, it is not optically active. And when we do the reaction with pentane, here we get 2 products which are achiral, that is 1-chloropentane, we do not have a chiral center here. And if I look into 3-chloropentane also, we do not have a chiral center here. But what if we look into this molecule which is 2-chloropentane? Here we have generated a chiral center. This center is chiral because in this the carbon is attached to 4 different groups. One is chlorine, here we have methyl, and then here we have a propyl group. So this is a chiral center. Now what will happen to the stereochemistry of this reaction? So supposing if we start with a molecule which is achiral and we end up in a molecule which is chiral, then in that case the compound formed or the product formed will be a racemic mixture. What is a racemic mixture? Please remember, when we talk of optically active compounds, we say they are dextrorotatory, that is, they will rotate the plane of plane polarized light in right hand direction. If the molecule is levorotatory, it will rotate the plane of plane polarized light in left hand direction. And if the mixture is racemic, what we mean there is that that mixture is equimolar mixture of the dextro form and the levo form. So if the starting compound is optically inactive and the reagent is also optically inactive and we get an optically active compound, we generate a chiral carbon, a chiral center in the product, then in that case our product will be a racemic mixture. Let us go back to the geometry of the free radical. What is the structure of free radical? If you remember, I had told you that free radical is planar. So if this is planar, trigonal planar radical, so what we find here is that the probability of this Cl which will react, it will react equally at 2 phases. It can react either at this phase or it can react at this phase. So when it reacts at this phase, what we get here is we get S2 chloropropane. Here the chances of probability of the reaction are equal, and the other 50% chance is that it will take place at this phase. So what are we getting here is we are getting a mixture of enantiomers. We are getting a mixture of S form and the R form. I have not written here the dextro and the levo. What we have given here is the configuration of the molecule, which will be, I will be clarifying in the later lectures, the difference between the small d and the capital D, small l and the capital N, and here I am talking about the absolute configuration. So when I talk of the absolute configuration, what we find here is Cl is on the left hand side and here the Cl is on the right hand side. So what we say that these two molecules have opposite configuration, and of course when we have to do the R and the S, I just cannot randomly say because the Cl is on the right hand side, therefore it is the R configuration. This configuration has to be assigned on the basis of Khan and Prelog's rules of giving priority to these groups, which again we will be discussing in our later lectures. So when the molecule is achiral, reagent is achiral, and we get a chiral molecule, then in that case the reaction is accompanied by racemization because this structure is planar and the reaction can take place from either side. Now supposing, now we have a molecule which already has a chiral center in it. For example, here this carbon is chiral, that is, it is attached to 4 different groups here, that is CH3 here, H here, Cl here, and then we have a propyl group here. So this molecule is chiral. Now again, if a reaction will take place here, it will generate another chiral molecule, another chiral center here. But now here what we find is that the probability of reaction is not equal, and we will get 2 centers here. Here we are getting 2 diastereomers, here we are getting 2 diastereomers, we are getting 2 chiral centers and we are getting 2 diastereomers. So these we are generating optically active isomers here, this and this. The physical properties of the diastereomers are different. That is, the boiling point will be different. If they are solids, their melting point will be different. So we will be able to separate these 2 diastereomers. So what we've seen that if a molecule is optically active and then if we do halogenation and the reaction intermediate formed is free radical, then we end up with diastereomers which can be separated. What are diastereomers? Diastereomers are stereoisomers which may be optically active or which may not be optically active, and they are not superimposable mirror images of each other, and then we can have different properties also. Now if we go on to next point, so what if I summarize this reaction now? So what we know is that if we talk of halogenation of alkanes, then halogenation of alkanes is a free radical reaction. Since it is a free radical reaction, we get a mixture of products, that is we get one chloro, dichloro, trichloro, tetrachloro. And if we talk of a higher alkane, then the probability of getting different products is too great. And if we talk of the order of reactivity of halogens, then it is fluorination greater than chlorination, greater than bromination and iodination. And if we talk of the reactivity of hydrogens, then the order of reactivity of hydrogen is tertiary, greater than secondary, greater than primary. So this is what when we were talking about alkanes. What if we talk of benzylic reactions or allylic reactions? If we talk of a benzylic reaction or an allylic substitution, then what we have here is we get here this compound. So this is, now please remember in this molecule what we have here, till now we've talked of the saturated compounds. Here now we are talking of an unsaturated compound. So when I talk of this unsaturated compound, here we have a double bond where the reactions will take place at room temperature. And here we have a alkyl group where the reaction requirement is again either the reaction will take place at high temperature or it will take place in presence of light. So this reaction, when we talk of this reaction, this is an allylic position. And what I will be talking here is allylic substitution. So when chlorine reacts with propene, what we get here is allyl chloride. Similarly, if I talk of SO2Cl2, this also brings about allylic chlorination. This is a specific reagent for allylic substitution, and this is a very good reagent because the side products that we get here are SO2 and HCl, which are gaseous. So the problem of separating the products also will not arise. The other reagent with which we can bring about bromination very nicely at allylic position is N-bromosuccinimide. N-bromosuccinimide also undergoes homolytic cleavage to give us Br free radicals, which will bring about allylic substitution. Now, if I talk of allylic substitution, please remember here we have two allylic positions. A allylic position is that position which is adjacent to the double bond. So I have an allylic hydrogen here and I have an allylic hydrogen here. Now the question will arise, which allylic hydrogen will be more reactive? Then please remember this is going to be more reactive since this will be secondary allyl group and this will be stable because of hyperconjugation here and because of resonance effect here. Whereas in this case the chances of hyperconjugation are not much, or they are no hyperconjugate, they are not much here. So now what we see is, and if I talk of this substitution, which is again benzylic substitution, we can bring about this with NBS. Now please remember this molecule can undergo two types of reactions. One is bromination at this. This is a free radical substitution reaction. So this will bring about benzylic bromination. Whereas if we talk of the ring, if I talk of the ring here, then here this is an example of electrophilic substitution reaction. So these two reaction mechanisms are very, very different. This is electrophilic, this is free radical substitution. So when we add NBS to it, it will generate a Br free radical which will bring about substitution here. Whereas when I talk of this will give me a Br plus, that is an electrophile which will come and substitute a hydrogen here, which is an electrophilic substitution, and we get two products, ortho and the para-bromo ethyl benzene. Now if we go on to these two reactions only, these reactions only. So these were the reactions of free radical substitution reactions. So free radical substitution reactions are taking place at the alkyl group, right? Now another type of reactions which involve radical mechanisms are free radical addition reactions. That is, at this point the reaction may be normally, please remember, the normal reaction here is an electrophilic reaction. That is because this area is rich in electrons. So what will come and attack here is the electrophile. Electrophile will initiate the reaction. This is a normal reaction, now normal course of reaction, which is electrophilic reaction, in which Markovnikov rule is followed. Markovnikov rule says that the negative part of the reagent will go to that carbon which is having less number of hydrogens. So I would just like to, before I go into the mechanism of free radical addition reactions, I would like to take up this example and clear few concepts here. See, if we are doing the reaction normally, not in presence of a reagent, in presence of peroxide, then HBr will add across the double bond according to Markovnikov's rule. That is, the reagent here is unsymmetrical. It is made up of two different atoms. The alkene here is unsymmetrical. It is, the groups on the either side are different. Here we have two hydrogens, here we have methyl. So the group and a hydrogen here, so these groups are different. So this is an unsymmetrical alkene. So when we talk of Markovnikov's rule, it says that the reagent will act across the double bond in such a manner so that the negative part of the reagent goes to that carbon which is having less number of hydrogens. So what do we observe here is that if I look into this molecule here, so what I find here, that negative part is going to that carbon which is having less number of hydrogens here, and we get 2-bromopropane. This mechanism we will be discussing in detail later on. But supposing if we add peroxide to the reaction mixture, then a very abnormal, a very different product was formed. Nobody could offer any explanation for this until later on it was given by Kharash, and he said this effect, to this he said a peroxide effect. In this what he observed was, in presence of a peroxide, the regioselectivity of the reaction changes, that now the negative part of the reagent goes to that carbon which is having more number of hydrogens. What I mean here is, we have to look into the double bond, the hydrogens across the double bond. So this is less number. When the negative part goes here, then this is following Markovnikov's rule, and when the negative part goes here, it is following the peroxide effect or the Kharash effect. And we will be discussing this in my next lecture on the basis of, again, the bond dissociation energies only, that why only HBr undergoes free radical reactions, free radical additions. HCl, HF, HI, these molecules do not give us anti-Markovnikov product. So what we say now is that free radicals not only bring about substitution, they can also bring about free radical addition reactions. Now what we see here is, these free radical addition reactions are brought only in presence of a peroxide. As halogens have low dissociation energy, similarly what we find here is that this oxygen bond here, also here the energy of dissociation is low. It is 150 kilojoules per mole. So what happens is, this bond cleaves very readily to give us this free radical, that is alkoxy free radical. So this is the initiation step. Please remember, whether we talk of substitution or addition reactions, we will be even talking of petroleum later on, how we get diesel and lower hydrocarbons from cracking of petroleum. All these will involve free radicals, and all of these reactions will involve three basic steps, that is chain initiation, which is an endothermic reaction, chain then the propagation, which is exothermic, and then of course the termination step. So here this molecule breaks down and it initiates the reaction, and what we get here is two alkoxy free radicals. These two alkoxy free radicals, one among them goes and reacts with HBr here. And what it does, it abstracts a hydrogen from here. Please remember, it will turn into a molecule, and in turn it will generate a free radical here. Now this free radical here, the energy of activation here is low, and the bond energy also, heat of energy also, what we find, the heat of reaction here is also low, that is, this is an exothermic reaction. So overall reaction is, this is a favorable reaction for the reaction to proceed further. Now this Br free radical goes and reacts with propene here across this double bond. Now when we see, now here the chances are, we have two probabilities here. This free radical can go and form a bond here, in which case we will get a secondary free radical, or this free radical can go and form a bond here, in which case we will get a primary free radical. This bond will cleave here homolytically. Please remember, this is breaking here homolytically. So one of the electrons here is involved in bond formation with bromine, whereas other electron is going to either of the carbons here. So but what we know here is that the secondary free radical is more stable than a primary free radical, and hence we get this. So the probability that we are getting this molecule, the product 1-bromopropane, is high, and we do not get 2-bromopropane because the secondary, the primary free radical is not stable. So now what happens is, in the next step, which is the next step in this free radical, the secondary free radical here goes and reacts with HBr. It will abstract H from here, converting into bromopropane, and in turn it generates another free radical, which is a Br free radical, and in such a manner this reaction continues. So what we've seen here is a free radical mechanism. In my next lecture, or I would now like to discuss with you the electrophilic addition reactions also, which will be summing up in my next class, so that you can know the difference between the peroxide effect and normal Markovnikov's rule. Hope this lecture has been useful for you, and you've been able to correlate the energy changes involved in a free radical reaction along with the mechanism of the reaction.
Definitely, I would say this lecture would have been very useful for the students, because sometimes all those students who tend to skip their classes or used to bunk their classes, with the help of these lectures, it would be easier for them to recall all what they have learnt or not learnt through their books. Dear friends, if you have any queries, you can mail us at info.cc@nic.in, or if you have any question regarding this very topic, you can mail us, so that the next time when Dr. Aparajita comes to our studio, we would love to solve your queries with the help of these lectures. And I would like to tell you all that if you want to access this particular lecture, then you have YouTube, on which we daily upload our lectures. Thank you, ma'am. Thank you so very much.